Hi, hello everyone. Welcome. My name is Kristoffer. I'm a software developer at Gradient Software, and I've been working with Gadgetron for a couple of years now. As part of my work with Gadgetron, I have actually I've been building this external language interface that we're going to talk about today. Yeah. So the external language interface, it's primarily a tool for prototyping. This is the only slide in my talk. I figured, like as an introduction, that we should build a prototype using the external language interface, which is actually build a thing. So I'm going to take you down to MATLAB, and we're going to put some code together, and we're going to talk about the external language interface as the components sort of come up naturally. Oliver, I think, is on hand to handle questions, but I do not have a lot of time, so I don't know how many we'll get to. But like, ask them in Slack, and I'll make sure everyone gets an answer, even though I might not get to them during the talk. You can follow along at home. Like, I've put some materials on the course site. There's some files describing sort of where I want to end up. But keep in mind, this is just going to be me live coding and you trying to to help out, maybe. So I might not end up exactly where the files are in the repository. They're just there sort of as a guide. You should be able to follow along, even though I have to keep the pace high. You can also follow along in Python. So I'm gonna do this in MATLAB, but the Python functions are the same. They have the same name and the same package. They take the same arguments. They return the same thing. So that should work for you as well. Like, you might have to be a little creative sometimes, but generally the interfaces are completely the same, except when they're better in Python. So you can iterate a connection. You don't have to call next, for instance. But, you should be able to follow along. It's just I have to keep the pace pretty high. Let me introduce my workspace, I guess. So down here, I have two terminals, kind of like the first day. So on the left here, I'll be running my Gadgetron client. This is my demo directory. And on the right here, I'll be running Gadgetron. I have taken great care. You see, I've navigated this terminal to the same directory. That's where I'll be running the client and where I keep the code. This is to let, like later in the talk, hopefully I'll have created some images. Hopefully everything is working. And I'll want Gadgetron to run MATLAB for me. And when Gadgetron is running in this folder, it will run MATLAB in this folder. And that means MATLAB will see the code we have written. So yeah, I've very carefully navigated Gadgetron into this folder, and we're going to run Gadgetron. We're not going to pay a lot of attention to Gadgetron this talk. It's just going to sit here quietly. Like, we might have a look at the logs once in a while, but most of the time it's just going to live in this terminal, and it's going to be hidden by this. This is my editor, where I keep my config file. So, like, the workflow will sort of mirror the workflow from the talk I did day one. So we will run the client, send our data set, and we will update our config file in between. So the client command won't change, but our config file will change, and our MATLAB code will change. Down here in the basement, I have MATLAB. Hopefully this is familiar to all of you. If not, then I guess you will become familiar with MATLAB. So up here in my folder, my working demo folder, I have my data set. It's the same as the one I used the first week. It's a fully sampled Cartesian data set. It has 10 repetitions. Someone put a phantom in a scanner and did this set. It has some Siemens artifacts, so there's some oversampling in the readout direction, for instance, that we'll deal with at some point. I also have the config file we'll be writing. Then there's this plus demo folder. The plus is MATLAB. It means MATLAB will pick this up as a package. So it's a demo package. And if I list the contents, you see there's this handle connection function in there. And these are just sort of where I hope to go, where I hope to be at different stages in my talk, so I can maybe sneak a peek and have some help if things don't go well. I don't plan to use them. All that really matters for the demo is this handle connection function. So that's sort of that's the structure of our folders. Down here in MATLAB, you see I have navigated to the demo folder, but otherwise, this is just an entirely clean MATLAB. I thought the first thing we would do would actually be to install the external language interface. So I'm going to go here, click Home, and click Add-ons, and see if I can't find my Gadgetron package. I'm just going to search for Gadgetron, and this shows up. This is my package. I like it. I'm just going to click Add. Let's see if I can remember my password. Everyone is happy. I own your children. Don't worry about this. It's going to be fine. We also don't need to read anything because we actually know what's going on here. That's it. The interface is now installed. You have other options. You can install from source if you like. But you just want to get like hacking away, prototyping, working on some data, and installing the package is by far the easiest way to get going. It gets regular updates from me, like every time I fix a bug or someone else does, and the package is updated, and you don't have to bother. Yeah, so that's a great option. Yeah, so to get started, let's see if we can't get some data over here in MATLAB. So we need data somehow from this saved data set. We need to go through Gadgetron, and we need to go into MATLAB. And I think the thing to understand at this point is that the external language interface is just an MRD server implemented in an appropriate language. So the MATLAB external interface is just an MRD server. Gadgetron is just an MRD server. The Python interface is just an MRD server. The MATLAB MRD server is implemented in MATLAB. Python is implemented in Python. So we need to start a server here in MATLAB, and we need to direct Gadgetron to connect to it. We're going to start, I guess, up here in the config, telling Gadgetron to connect to our server. You see, this is a config file. It's not entirely empty, but it contains nothing interesting, really. So I've added an acquisition reader, so we can get acquisitions from the data set. Currently, the stream is empty, so the acquisitions just pass right through, and then there's an image writer. Hopefully, we can write some images at some point. But to get a connection to an MRD server somewhere else, we're going to add an external block here. We have options here. We can either start a process or connect to a server. And we're going to connect to our MATLAB server. Connect takes a port, and we're going to use 18,000. I think that's sort of canonical. So this should do on the Gadgetron side. So we're going to get some acquisitions in. They're going to go in the stream. The stream is just a connection to MATLAB. So the acquisitions are going to queue up here before the MATLAB gadget, where they'll be available to us. Down here in MATLAB, to start the MRD server, we're going to call a function that's called listen. It tells the Gadgetron external interface to start a server and listen on a specific port. Gadgetron external listen. We're gonna use the same port, so 18,000. I'm gonna make sure those match up, so 18,000. And then we have to specify a function here. So listen will go away. We'll lose interactivity in the console. Basically, it's waiting for a connection. And whenever a connection is established, listen will prepare a connection object for us. That's sort of the connection sort of models the connection to Gadgetron. So it's like an object you use to interact with Gadgetron. So listen will prepare that object for us and then call the function we specify with a connection as an argument. I've prepared this handle connection function. It doesn't do anything. It just takes a connection as an argument, and we would like to have it called. It's in the demo package, so it's demo.handle connection. As I execute this, we see like listen prints out a few things. It tells me it's ready to take a connection on port 18,000. So if we send this config file through Gadgetron, we should see a connection appear. So we're going to run the client here, Gadgetron client. It needs a data set. We're going to give it simply. And it needs a config file. We're going to send our config file. If we have a brief look at the Gadgetron log, we see the connection made to MATLAB. And we see in MATLAB, we see the function has returned. We got our console back, but nothing happened because this this function is pretty empty, so it doesn't do anything very useful. But we have a connection. And MATLAB being interactive, this being a process we control, we can sort of set a breakpoint and actually have a look around. So I'm going to set a breakpoint. I'm going to rerun this, and I'm going to resend the data set. So now we hit the breakpoint. MATLAB grabs focus, and this underscore, this 3 here means we're stuck on line 3. You can see, our list of symbols, we have the connection here. So we can have a look at the connection, and we can even ask for some help here, because someone has written nice descriptive text and help messages for the MATLAB package. If you're in Python, you'll have to wait a few weeks. And for MATLAB, we actually have proper documentation. So this is the connection object. It is the object through which we interact with Gadgetron from MATLAB. It's not very complicated. There's actually there's not a lot of stuff going on here. It has a few properties. We saw the properties we printed out when we printed out the connection object. These are the MRD headers. It's the stuff that is sent in an MRD stream before the data. So config is like the MRD configuration. It is very analogous to the config file sent to Gadgetron. In fact, if we look closely, we see the config file here is an empty string, and someone thinks it's XML. It's an XML empty string. It is, in fact, the configuration from the external block here. So you can add configuration here and have it sent to MATLAB. We're not going to use it for anything, and it's a raw byte stream because that's a byte string, because that's what MRD specifies. But it's an option we have. We also have the header. It's the MRD data header, so it's the XML that accompanies the data set. If we were to take a look at it, we see that it's actually in the MATLAB interface represented nicely as a nested MATLAB structure. So we could sort of dig into the header and access information about the experiment before we get to the data. So these MRD headers are available on the connection. And then there's a number of functions. We're going to focus on next and send, because these are like the meat of the connection. You use next to retrieve an item from Gadgetron, and you use send to send an item back. And that is essentially all there is to it. Filter is used to sort of filter out items if you don't want next to return them. So you can say, if you use filter, you can specify that you don't want waveforms, for instance, if there's waveforms in your data, and then you just get acquisitions. We won't use it, but it's there as an option. And then there's a couple of functions here that lets you modify the reader and the writer set. I'm not going to go into great detail, but it means that you have control over the functions that turn the binary MRD data into items in MATLAB. It means that the items returned from next are in fact highly configurable. So if you're unhappy with my implementation of image array and the data type there, you can substitute your own. That is just an array of images, a cell array of images. So that makes the connection object here like very flexible and configurable. But for this prototype session, we're just going to use the default reader and writer set and not worry too much about it. We have a connection here in our hands. So I think we should call next. Calling next, it fetches like an item from Gadgetron. So all our acquisitions are sort of queued up here before external. And when we call next, we read in one of them. You see we get a nice acquisition object with a header and data and an empty trajectory here. And we can we can have a look at the header. We get a nice MATLAB structure with all the header information. If we notice the scan counter is 1, we can request the next acquisition, and we can look at its header, and we can see it's a different acquisition. The scan counter is 2. So by calling next repeatedly, we can fetch the data from Gadgetron, basically. So we have access to our data set. Yeah, so that's all good. We have a data set. We can use the client to replay it. We can send it through Gadgetron, and we have access to it in MATLAB. Now we just need to use it. Now we need to build a prototype here. We need to build something, and I'm gonna build like a simple reconstruction. I'm gonna just do an inverse FFT and a simple coil combiner sum of squares. But for this talk, we're gonna pretend that that's like an awesome reconstruction. It's like the prototype you wanted to build. It's like it's a top-notch, excellent thing. The following talks will have like much more advanced, I guess, reconstructions. They're doing better things. But for now, we're just going to keep it simple so we can sort of focus on the process, focus on the interface, so we can talk about what's going on. The plan here is that I want to build k-space buffers. I want to do an inverse FFT. I want to combine the channels, and then I want to return an image to Gadgetron. So I guess our first task here in our handle connection function is going to be to build a k-space buffer. So I could read the acquisitions one at a time. I could look at their headers, and I could try to fit them into an array in the correct place. But it just so happens that Gadgetron is an excellent tool, and it's full of functionality that we can just use, right? So I'm just going to add a couple of gadgets here that will build a k-space buffer for me. Class name. The gadgets we're going to use, of course, are the impeccable acquisition accumulate trigger gadget. It lives in Gadgetron MRI core. And we're going to follow up with bucket to buffer, because that's going to give us, hopefully I can spell. So acquisition accumulate trigger gadget is going to bundle up acquisitions, and bucket to buffer is going to create nice k-space buffers. We have to configure acquisition accumulate trigger gadget a little, so we have to add a property here to tell it to trigger on each repetition. There's 10 repetitions in the data set. So trigger dimension is going to be repetition set there. Hopefully, if we have not spelled too horribly, this should just run. So we've not changed any code at all. We're just gonna set MATLAB listening again. Otherwise, Gadgetron can't connect, and it takes that quite personally. And then we're gonna run this new config file. We hit our breakpoint here. We still have a connection. But if we call connection next, we see that we no longer have acquisitions as our input. We actually get recon data. If you recall from week 1, recon data is sort of assembled k-space buffers. It's a venerable type in Gadgetron. It has a lot of uses, a lot of stakeholders. So there's a lot of, it's not easy to get to the data, but we have it here in MATLAB, and we can quite easily sort of take a look at it. So we see recon data. Let's say recon data. We're going to grab a new one, connection next. And then we can go recon data bits. We can see, so recon data is made out of bits. We have 1 bit here, and then we can dot buffer that. And you can see, oh, so if you dot your way into recon data enough, you get to like the data. This is our k-space array. So we have 256 samples in the readout direction. We have 128 acquisitions, and we have 32 channels. There's also a structure of headers here. So we're going to have a look at the headers. And you see this is a MATLAB struct. We get all the header fields. So we get sort of the first dimension here is the dimensionality of the header field. And then we have 128 samples because we have 128 acquisitions. So we sort of get this fully assembled recon data K-space buffer by just leveraging the functionality in Gadgetron. Gadgetron is there, it's ready, it's prepared to do all the work for us essentially. So to do our reconstruction, I'm gonna return to the code here. We are gonna grab a recon data from the connection. This gives us recon data, and then we're gonna dig out the data. It lives in recon data, bits, buffer, data. Yeah, let's rerun here. Iteratively, right? So now we have both data and recon data. If we print the size of our data, we see we have quite happily obtained the K-space buffer. Yeah. So what we need to do to make an image, we need to do an FFT, and we need to combine the channels. We can do this interactively. I'm going to do it here. Right? So MATLAB has a number of FFT functions, and I don't really like any of them. I didn't write my own, but I have wrapped them up in an ISO interface as a utility function, actually in the Gadgetron package. So I'm going to call that instead. You could easily do this with the MATLAB FFT functions. I mean, under the hood, it's the MATLAB FFT functions, but I'm going to call this this function instead because it's more delicious. So Gadgetron lib FFT, I think, and we'd like to call a centered inverse FFT in n dimensions. It operates on our data. The dimensions we're interested in, so we have the readout dimension, and then we have the first encoding dimension, the phase encoding, and this is E2 dimension. We have flat images, so it's singleton, and then these are channels. We would like to do an FFT along the first 3 dimensions, and whatever comes out of that, we just cannot assign that back in the data array. So if we run this, we should hit our breakpoint, and data should now actually contain a complex image for each channel. So we could potentially plot them already. So I want apps of data, I want the image dimensions, and then I want the first channel, something like this. And so we see this is the reconstructed image of the first channel in our data. All right. So far, so good. Then, of course, we have to combine all the channels to get a single image and then send that image back to the client. So to combine the channels, I'm just going to do a simple like sum of squares. So I would like the square root of the sum of the square of the apps of data, please. Square doesn't exist in sum. We have to sum along the channel dimension. I believe that is 4 in this case. There we are. Square is not a function. It doesn't actually exist. So I have to invent square here. I'm going to implement it as a lambda function. We're going to see a lot of those. I'm going to use an @. It tells MATLAB I'm doing funny function stuff. I'm going to take an argument x, and to do square, I would like MATLAB to just square every element in x. So this is a nice lambda function. It's very short to write. It's a function without a name, which I'm then promptly going to give a name. I'm going to call it square. So if I run this now, I should no longer have, so my data array is no longer So it has still a singleton third dimension, MATLAB doesn't bother, and it has a singleton fourth dimension, and MATLAB doesn't bother. So we've collapsed all the channels, we've combined them all. So now we just have a pretty simple array here full of image data. We should be able to show that. It's also no longer complex. So we can just stick data into imshow and have a look at where we are, have a look at our image. Excellent, pretty good. We see the oversampling here. So the readout direction is vertical here, and we see there's a lot of blank space here. So why don't we get rid of that? We could fiddle around in MATLAB, I guess, but Gadgetron is a wonderful toolbox. It has a lot of things in it that can help us out. So we're just gonna stick a gadget in here. That'll help us with the oversampling. So it lives in MRI core, almost of course, class name. And this gadget, it removes the readout oversampling. So it's called remove readout oversampling gadget. And if I rerun this and rerun the client, our data now, if I plot it, is nicely cropped to the 128 by 128 image specified in the image header. So by just leveraging the functionality in Gadgetron, we can solve some problems pretty quickly. So far so good. We have images. We're very much not done though. So we're not sending anything back to the client. And we're also just processing the first repetition. But we'll deal with those. I guess we'll solve the problems one at a time. First, let us send an image back to the client. As it turns out, that is the biggest hurdle here. So to send an image back to Gadgetron, we want to call connection send with some sort of image. Send looks at its argument. It checks its type really, and then it selects a writer based on that. So it has a set of writers. Each has a predicate. So it will offer the item to each writer. And if a writer accepts the item, it'll be chosen and it'll write the binary data into the MRD stream and it'll go back to Gadgetron. So we have to have an image here of a type for which there is a writer. And the MATLAB interface at the moment is pretty sparse in writers. That's going to change, but right now we only support the MRD types. So we can pick acquisition, and we can pick waveform, and we can pick image. Luckily, image is probably going to be pretty good for us as we are working in images. So that's going to work out nicely. We'll just have to initialize a data structure, an image object. It's going to have, it's going to be of this type, image. There we are. So we're going to have to create a Gadgetron types image in some way. And we have a lot of options. Like it has a constructor that just creates a thing, and we can build our own header and put some data in there. It's not hard, but it's a bit fiddly. So I'm going to use a convenience method instead. It's called image Gadgetron types image from data. And this from data function is a static function on image, and it takes a few arguments. So it takes some data, and it takes a reference acquisition header. So in the MRD types, in the MRD standard, the image header is full of a lot of metadata, and a lot of it can sort of be filled in if you know the header of one of the acquisitions that we use to produce the image. So this is sort of a shortcut. We can fill in a lot of the image header if we just have an acquisition header to use as a base. So we need to get our hands on some sort of image data, and we need to get our hands on some sort of reference acquisition. Let's go data first, right? Some would say we could use our data. That would be very convenient, but the Kristoffer who wrote this function, it's me from about a year in the past, he had this notion that in fact channels were first. So he was working like, I don't know why, but he thought image data would be channel XYZ, and the image data we actually have is XYZ channels. So to make Kristoffer from the past happy, we have to permute our data a little. So we have to pick channels first and then XYZ. What that should do for data. And then we have to somehow get our hands on an acquisition header. If you recall, there's a lot of headers in the recon data. So perhaps if we pretend that there's a function that will take a recon data and then produce an appropriate header. Let's pretend that exists and then just use that. So reference from recon data. That sounds nice. Recon data, recon data. And then that should work, except someone really, really very much too lazy has forgotten to build this reference from recon data function. So we're going to have to do that. Function. So it returns a reference, and it's called reference from recon data. It's going to live down here in anonymous function space in MATLAB. But we're going to pretend that some of these functions are good enough to be library functions. And at some point, we're going to move them out where our colleagues can get at them because we want to be nice. But I'm going to keep everything in this file for like simplicity. But yeah, let's set a breakpoint and then see if we can't build this function. We're going to run. We're going to hit our breakpoint here, so we can sort of evaluate our recon data here. It has bits, and they have buffers. And I guess we have this header array. Headers. We have this header array. Right? So we need here to make a function that, for each field in this structure, will select an acquisition and then give us everything along the first dimension here. This is either really, really simple or really, really fiddly. I'm going to do this in a one-liner, but there's going to be a lot of things going on here. Essentially, we're going to call struct fun because everything is better with the fun functions. So we're going to return a reference here, and we're going to call it struct fun. Struct fun, yeah. So we would like a structure returned. Right? We would like a structure with the same fields. We don't need an array. So we're going to tell MATLAB that the output is not uniform. Uniform output. It's going to be false. And then we need to operate on some data. We want to operate on, of course, recon data. .bits, .buffer, .headers. And that should be the header array. And then we need to specify like a function. So the function will be called for each element. The output, so the key in the output structure will be whatever we return from this function given this input. So for some input k, we would like to take everything from the last acquisition. So this should potentially give us, if I spelled everything correctly, this should give us a lovely, lovely reference header that we could use to build an image, and then the image can be sent back to the client. So let's run this. And if we have a look in our folder here, we see there's no output. The client writes out at age 5 if it gets output from Gadgetron. So we run this. This completes. That's nice. We're a little short on logging output here, so I'm going to add a disp statement here. Disp sending image to client. There we are. But we see everything looks fine. And indeed, if you have a look over here, we now have an output file. So if we open that in our viewer, we actually have an excellent image returned to the client. Milestone, boys. So we have built a prototype that does a job and sends an image back to the client. There's still some issues though, right? So we can send an image now, but we're just processing the first repetition. If we want to handle all the images, we're going to do that properly later. Right now, we're just going to while through this. So as long as there's any input, please make an image and send it to the client, right? So if we run this now and run the client, yes, we see in MATLAB, we see a lot of logging output. We send a lot of images, and then we get this exception. This exception is thrown by next. So when we call next and the connection is empty, this exception is produced. And that sort of kills handle connection and everything shuts down nicely. So it's not actually a problem, it just doesn't look very nice. Up here in client land, we can have a look at our data set. So this is the first image. There's just one, but now we get all 10 repetition, all 10 repetitions. So that sort of takes care of that issue. However, along the way here, we've picked up pretty unpleasant qualities in our code, right? So these 3 lines here, I mean, they're just a simple FFT and some squares, but we're pretending that this is your super nice code. So this is 200 lines of MATLAB code that does excellent ghost correction or like something like that. And right now it's sort of stuck in the middle of a loop. It's mixed in with a lot of sort of code that deals with Gadgetron somehow. It's not very usable. So when your friend Bob at work wants to like borrow some of your code to do that thing, he will likely have to copy paste it. That means when you fix your bugs, his code is still broken, and he'll come to you for questions or answers, and you'll talk, and that's nice, but you're wasting time. So we want to make this a lot nicer. So essentially, we want to take all the code here that does any actual work, and we want to move it into toolboxes where it's easily reusable and easier to reason about. So we want a nice set of functions. And they should do just one thing, and they should do that thing like really well. And everything they need to do their job should be arguments, and the finished product should be returned. So we'll do our best to move everything out here. I'd also like to note that we're pretty damn close to like having a bunch of independent steps here. So this FFT doesn't really care about it doesn't care about what's going on around it. So it takes some data and it overwrites it. Again, this channel combination here takes some data and overwrites it, and image just takes some data and produces an image. So recon data is like an exception to this. We need recon data multiple places, but in fact, we only need to sort of get the reference header. So if we're a bit clever with our, I guess, function input, we see that we're very close to having like a bunch of toolbox functions that could be just composed using function composition. So we're going to try to take all the stuff in this while loop and then move it into appropriate toolbox functions. So first of all, I'm going to make sort of a buffer object, a buffer type that is the data we need to work on, and then I want to carry along this reference. So I'm going to make a function here. It's going to return a buffer, and it's called buffer from recon data. And it's going to take some recon data, and it's going to return a buffer. And on that buffer is some data. I guess I can just steal this. And then there's going to be a reference here, a reference and acquisition header, a reference acquisition header. And luckily, we already have a function that can give us one of those. We're just going to call that. So instead of just like extracting our data here, we're going to make a buffer by calling buffer from recon data of this recon data. Similarly, if we were to take all our beautiful work, our lovely 200 lines of MATLAB code that does beautiful ghost correction, and put it into a function here, it's going to output a buffer, but a process buffer, and then it's going to reconstruct buffer, I guess. It's going to take a buffer and write a buffer, and it's going to just do beautiful, beautiful work. So what we want to do in here is, instead of just, so there's no data anymore, but there's the data on the buffer. And we're gonna write that back on the buffer. And again, we're gonna coil combine the buffer data and just write that back. So we've taken like our beautiful algorithm and we've put it into a toolbox function. But we note that maybe this is not entirely general, right? So we have decided in this case that the image dimensions are the first 3 dimensions. And that's sort of hard-coded into this library function. And it actually doesn't have to be, right? So we can lift this up. So if we take FFT dims here, FFT dims, now it's sort of configurable. So if Bob, who has other opinions about which channels are, which dimension is going to be channels, if we lift this up, channel dim, if we lift these up, we can actually have him use our code as well. So we get sort of greater generality, and he has access to the bug fixes we make. Channel dim. That means when we call this function, we have to be a little specific though. So we construct buffer, takes our previous buffer, and then we have to specify where we want the FFT to happen, and that's still 1, 2, 3. And the 4th dimension is going to be the channels. So far, so good. Then we're going to add a function here. That's going to make an image from a buffer. It's called image from buffer. These are terrible. They're not terrible. They're actually good names. It's going to take a buffer, and it's going to make an image. Pretty simple. It's going to do essentially this. So we are no longer operating on just data. We are trying to use buffered data. And for reference, we can just read the reference on the buffer. So up here to create an image, we can just create an image. Image from buffer. Now, sort of if you have a look, there's some configuration going on, but this is very much just the output from one function serving as the input to the next. So we're very close to just putting everything together with the function composition. So it's going to be like function composition and some steps of configuration. We also note that there's some permutation going on here. We could parameterize this, lift it up as an argument. I guess that would be good for completeness, but it serves no real purpose in the demo, so I'm not going to do it. I guess, yeah, you should in your algorithm, I guess. And then finally, I want to make a function that doesn't return anything, but just sends an image to client. So to the client, so function send image to client. It takes an image, and it must take the connection. And it's just going to do this. Oh, sorry. So we can just call that up, yeah, send image to client image, and then we need to specify the connection. So we've changed the code a lot. We've moved everything out in nice functions where Bob can get at them and use them. but we've not changed the functionality much. So perhaps we should check that this still works and we still get images. So I'm gonna call listen, and I'm gonna send some data. We get sending image client still printed out. The client here returns, and we can have a look at 47. So we see the 47 data set has images in it still. So we didn't touch the functionality. We just prettied up the code. So we went from an ugly thing that works to a prettier thing that works. Yeah. What we want to do now, I guess, is to get rid of this ugly while loop and take this composition a step further. Right? We imagine that what we have now is a nice library of toolbox functions, and they, with fairly light work, can be composed to sort of build a transformation that takes the input data to the desired output. So we would like all the work, all the nitty-gritty details about which covariant matrices goes where, and that lives in the toolbox functions. Up here, when we're actually building our reconstruction, we just want to compose toolbox functions and include configuration that makes everything work smoothly. So I want to sort of, instead of this while true thing, I want to build a function. I want to build a series of functions that each produce an item that's closer to the desired output. I'm going to call them step functions. So my first step function, we just push this down a little. My first step is just going to be calling next on the connection. So at this point, if I call step at the cursor, I will just get recon data. I can then wrap this step function in a new step function. I'm going to call this step. This new step function can use the old step function to get recon data, and then it can transform the recon data into buffers. So I'm going to make this a lambda function, and it's going to call buffer from recon data, and it's going to use the first step function to actually obtain its recon data. So now we've sort of added a layer. When I call this function, it outputs a buffer, and it produces the buffer by obtaining recon data and turning the recon data into a buffer. We can layer more of our reconstruction here. We can reconstruct the buffer, and to obtain a buffer, we're just going to call step. So now if I call this, so these step functions are different. You're on top of that. If I call this step function, I'm going to have a reconstructed buffer. So I'm going to have an array of image data show up. And I can layer this further. So I can make a step function that produces an image from buffer. And it obtains reconstructed data by calling the previous step functions. So we're sort of, let's get rid of this. We're sort of layering functions. I guess we can run this and have a look at how we're doing it. So I'm going to start this. I'm going to return to the client, and I'm going to rerun. And we hit our breakpoint really, really quickly. So it's important to note that nobody is actually calling next here. All this code is doing is sort of building a chain of functions calling each other, but nobody actually calls them. However, if I here call step now, I'm going to call, sorry, I didn't call step, but step here, this is our final step. If I actually call step, I get an error because, of course, reconstruction, it takes some arguments, right? It needs to be configured to work in this context. So whenever I want to call reconstruct, I have to specify my dimensions. So I want the FFT, 1, 2, 3 dimension, and I want to combine along the fourth. Let's retry this. Oh, sorry, there we are. We hit the breakpoint, and if I call step now, you'll see this step function returns an image. And this image is produced, right? So it's the output from image from buffer. So basically, the data goes through the same steps as before, but they're now assembled using function composition. And the configuration is sort of included in the steps here. So in this part of the code now, I am not shuffling data around. I am not I'm not concerned. I'm only concerned with chaining my nice toolbox functions and sort of making sure everything lines up by configuring them correctly. If I add a final step here, I can add a step that sends an image to a client. Right? So send image to client. And that takes, of course, an image. And we get an image by calling step. And it takes our connection. So if I run this, make it to the breakpoint, when I call step, I get no output, but we see the text here. I have send an image to the client every step I take. So that's good. That's excellent. We could process all the images by having this step in a while true. That would take us back to the exception though. So I'm going to use a utility method that I put in the library to sort of deal with this case. It's called Gadgetron consume. And it takes a single argument that is a function. And consume will call this function forever in a while true loop. And then it will ignore the exception, the particular exception that's thrown from X. So if I give this step, it'll call step until we get the exception, and then it'll shut down nicely. I'm also going to add some timing here. Tick-tock. Right. So this, if we run this, should just be nice and sexy and produce all the images. And we have nice toolbox functions, and the composition up here is really very excellent. So let's run it. Let's have a look. We see the images going out, and having a look at the data set, we see our new images. They are all here. So we are pretty happy about that. Yes, excellent. So I've used Lambda functions here to sort of chain my toolbox functions and configure them. If this gets any more real world, so this is a small example. If it gets any more real world, you're probably going to want to move to like higher order functions. So you will have a function that takes a step and some sort of configuration, and it builds the next step. That's the way the examples are put together, the examples that ship with the external interface. But for this example, like it doesn't make sense. I can just make do with lambdas up here. But yeah, so we've written some nice code. We're happy with this reconstruction, but we don't want to run MATLAB, right? So I don't want to call listen every time I want to run this code. So we're going to tell Gadgetron to run this for us instead. So instead of connecting to our MATLAB process, we want Gadgetron to execute MATLAB on its own and run this function and close everything down nicely. So I'm going to add an execute block instead. We're going to get rid of connect. So Gadgetron needs to know what sort of process it is to run. So we're going to tell it we want it to run some MATLAB. And then we need to tell it which function is to run. And we would like it to call demo.handle connection. You recall that is the name of this function. Gadgetron can see this function because we very carefully ran Gadgetron in the correct directory. You can also add appropriate directories to the MATLAB path or install them as packages. Basically, there's no surprises. Gadgetron just runs MATLAB as if you type MATLAB into your console, and everything that works in MATLAB works the same when MATLAB is started by Gadgetron. But we'll see this particular file because we very carefully placed MATLAB. And we have to close this. So when we run this, Gadgetron will start a MATLAB instance, and that instance will call our function. do the work, and then it'll exit when it's done. So this MATLAB instance, just to make the point, we actually don't need anymore. So I'm just going to close MATLAB. So right now we have zero instances of MATLAB running. If I run this, see the log here. We see bucket to buffer working, and we see so this is bucket to buffer, everything working. And this, in fact, this line, this line, this line, it's the logging output from MATLAB, as we saw it in the MATLAB console. So that gets intermixed with the Gadgetron log when you run it in this mode. We also see everything running concurrently. So like we're still working on buffer number 5 when the first image is done in MATLAB, over in MATLAB. So we get sort of a nice concurrency. And we get images out over here. We've seen them a lot. I hope you trust me when I say we get them. So in summary, when we use the foreign language interface, we get a lot of things to work for us really very easily, right? So when we use the Gadgetron client to replay our dataset as if it were live, and we in our code treat the dataset as if it was live, it's very easy to write code that works online on the scanner. And we also get to leverage all the functionality in Gadgetron. So we can do pre-processing of the acquisitions. We can do post-processing of the image. We can have multiple external nodes. You're not limited to one or even one type. So I could have a MATLAB gadget here doing acquisition work, and I could have a Python gadget doing something else. So we just get to mix and match our own external work with the functionality in Gadgetron. And finally, once we have a working prototype, once we have written some code that we're like proud of and things will do well, we can very easily just shift a line in the config file and suddenly run our code in a very deployment-friendly way. Yeah, I find the external interface very good for prototyping. I hope you will too. I guess we have like half a minute for a question. Otherwise, I yield my time to the next speakers.
Thanks a lot, Kristoffer. I have a question for you, and could you show the function that is included in Gadgetron MATLAB, like the simple recon and
the example functions?
Yeah. Yes.
Sure, let me see if I can find those here. I'm not sure what we're waiting for. There we go. So in here, there's some examples. I guess simple recon is the simplest. So these steps are sort of higher order functions, but the principle is the same. So I pass a next function through these steps, and I sort of weave them together in a very long chain. And so we have some toolbox functions, and we have some some step functions that sort of binds them together. So the steps are almost gadgets, I guess. So the steps live in here. And there's a step here that, what I want to do, that noise adjusts, right? So it's a high order functions, because we can use like a closure here to have some state. But essentially it takes an input function and it returns an output function. So it sort of decorates a function with another layer of functionality. And that is the structure of these examples. So it's very analogous to what I did. It's just, it actually uses the full high order functions because we need to carry state around sometimes. Like, is there anything specific?
And no, not just to show that there are different way of coding. And can you also show the tinyrecon.m function? So
yes.
Just
so
to mention, yeah, that you can.
The tiny recon function is sort of, so this reconstruction is where we were halfway through my talk, essentially, right? So it has the reconstruction. It's almost the same code. but it's all wrapped up in like there's a while true here, and then there's a try end to get rid of the exception. So this is all you need to do, right? So the external interface does not impose this style of toolbox and step functions. That's something I would like you to do. But if you are comfortable just working in a loop and having 1,000 lines of MATLAB, just one line after each other, that'll work too. Right? So the interface is actually only the connection class. So I'm going to call your function, and I'm going to give you a connection. Like how you call next and how you call send is up to you. I just wanted you to see that there was a way that was better than maybe having 500 lines of code in a single loop.
Is there any other advantage to use the add function, the handle?
Sorry?
Except the coding part, is there any advantage for the user in terms of performance to use the way you present?
No, so the advantage is mostly like software related. And so you get nice toolbox functions that you can reuse in other contexts. It makes reuse a lot easier, so you don't copy paste code around. If you copy paste code around, you copy paste bugs everywhere, and fixing them one place gets real hard.
Yeah, I think Oliver and Stan will show us how to do such.
Yes.
And I have a last question, because it's really related. In Python, I never use the consume argument, and never.
No, so in Python you don't need consume. MATLAB is a very old language. It doesn't support iterators in any way. Like you can write a class that can fit in a for loop, but you have to tell MATLAB how many elements it's going to iterate over, and MATLAB would then request each element in turn. And we just do not know how many items we're going to produce from the connection. Right? So we might be in a context where we are like doing online reconstruction. We might be doing some sort of video, and we don't know how many frames we need to produce. We don't know how many repetitions there's going to be. So we cannot tell MATLAB how many elements we have waiting in the connection. So we cannot use a MATLAB for loop to iterate. Python is a modern language, and Python has a lot of great support for iterators. So we, of course, use that in the Python interface. You can call next. It works the same. But you can also just stick your connection in a for loop. That'll do all the nexting for you, and it'll just sort of give you each item one at a time. Right? So because Python is a more modern language, we can support all the modern features, and that makes the Python interface sometimes more pleasant to work with. Right?
Okay, I see. Was a question on Slack. Maybe we can pick at least the last one, and we'll go back to the QA session next. So, can you use both MATLAB interface in Python and in MATLAB in the same chain?
Yes, you can mix and match. They're isolated. So if you have, so I have a block here that executes a MATLAB function. I could repeat that a couple of times and call different MATLAB functions. Right? So handle connection 1, 2, 3 here. I could have one of them be a Python gadget. That's fine. I could have one of them connect out to my process. I can mix and match however I want. What happens in this case is that Gadgetron starts a MATLAB process for each. So if I run this chain, Gadgetron will start 3 instances of MATLAB, tell them to each run like a separate function, and then close down nicely. That means like everything is as perfectly isolated as I can make it. You cannot edit a global variable to transfer state. For Python, this means that you don't rely on import orders. So the old Python interface had problems where if you have multiple Python gadgets and your imports were bad, they would sometimes clash, and that would be hard to fix. But everything now is nicely isolated. So you get a separate process for each, and they do not interfere.
And And I think I know the answer, but can it be different IP?
Yes, yeah. So if you want to connect, let's say this is connect. So I'm gonna see if this can be XML as well. So I use the port. There's also address. It defaults to localhost, but you can stick whatever you want in there. Right? So if you are running Gadgetron in a Docker container and MATLAB outside, you can just stick in your outside IP, or I guess share the host network, or whatever else you want, basically. So you can, you can add an IP. It'll just phone up and it'll just work. Yeah.
Okay, thanks a lot. I think it will be really helpful for everybody.